on using machine learning to forecast the performance of jobs while still in the queue. My name is Ian Costello, and here's a quick introduction. I am a current junior at the University of Maryland studying computer science and mathematics. I worked with Abhinav Patel, an assistant professor in the Department of Computer Science at the University of Maryland College Park. Previously, Abhinav was a computer scientist in the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. So the problem that we're trying to take on is that performance variability is a real concern on HPC systems, leading to slower scientific results and higher costs. In the graph below, you see the relative job performance of 4 sample applications over the course of 4 months running on Cori at NERSC. Despite running the exact same executable with the exact same input, the performance often differs greatly from the optimum. To address this variability, we will primarily focus on variability arising from suboptimal communication on the system due to network congestion. For example, packets may stall upon leaving a processor tile due to a full buffer from high congestion on a particular link. We set up and ran controlled experiments over the course of 4 months on a Dragonfly-based system, Cori. We submit the same applications periodically and collect various network hardware counters and apply various reductions to them and use machine learning to analyze the gathered performance data. The Dragonfly network, which is used at Cori at NERSC, which is a Cray XC40 system with 34 groups, consists of 96 groupings of 96 Aries routers into a logical group, where all routers in a group and all routers in a column are all connected. And then there's additional links which connect routers across groups on the system. The Aries router is specific to Cori, but our method is generally applicable. So to collect performance data, we ran 3 applications, AMG, Milk, and MiniVite. AMG and Milk were on 128 and 256 node counts, while MiniVite was solely on 128 nodes. And these are applications that are somewhat representative of typical HPC workloads with different communication versus computation profiles. For each job, we collect a massive swath of network counter data, job placement information, and the total execution time, which we use as input for our machine learning models. We segment our data into 2 primary categories: all routers, which consists of all the routers on the system, which only system admins have access to, and my routers, for example, the routers that the job actually was running on, which is available to individual users through libraries such as Aries and CL. The first analysis that we perform is attempting to predict the entire execution time of a scene application using system data strictly before the run. And so for each application and grouping, we train our model on system data and placement strictly before execution of the job time begins, simulating what a job scheduler would maybe predict on a job sitting in the queue, and evaluate it on a test set to predict the total execution time. So we are training on one data set, for example, AMG 128, and also evaluating on AMG 128, but we separate out a testing and a training data set. And then we further rigorously evaluate these models using recursive feature elimination to study which inputs are dominant predictors of performance. So for our first results, in order to understand the significance of different router groupings in predicting performance, we created gradient-boosted regressor models for each application dataset using 3 different router groups: my routers, IO routers, and all compute routers. We see particularly strong results with the my routers and all routers, which is particularly promising given that this kind of hits 2 different use cases for an individual user and for system administrators. And so we see strong error even though this data is strictly before the beginning of the execution of the job, with a MAPE between 5 to 10% and a PSLE less than 5% for MAPE and between 15 and 20% for Milk. So the second analysis that we performed is looking at which features are dominant predictors of performance. And so we use a technique called recursive feature elimination, where we train a full model, evaluate which features are dominant predictors, and then drop the least important predictor, and we repeat this process until all features are eliminated. And so in this graph on the left, you see the most important features when using the My Routers grouping versus using the All Routers grouping. And we see that the stalls on router tiles, RT packets response, and stalls on global links, RT stalls global, processor tile flits, and processor tile stalls are dominant predictors. And then it's not surprising that job performance depends on stalls on router and processor tiles, specifically on stalls on global links. For both applications, performance also depends on the number of flits sent on processor tiles. In our second analysis, we look to push the generalizability of our model. Instead of training and testing on a singular application dataset, we instead look to train on multiple datasets and test on an entirely distinct dataset. Our model uses no application-specific features and simply outputs a normalized guess of the performance of an input job. While having to account for multiple models adds complexity, it also vastly increases the amount and robustness of data available, which allowed us to train more tunable neural networks and other more complex machine learning models. And so here's our results. These graphs show the error of a testing set when it was entirely excluded for training. For example, on the first column on the left chart, you see AMG 128, and this means that AMG 128 was entirely excluded from training of our data sets. So we trained on AMG 512 and the two milk data sets, and then evaluated the error solely on AMG 128. And surprisingly, we see even better results even though this data set was excluded from training entirely. The MAPE for AMG 128 reduces from 4.23 to 3.61, and for milk 512, it reduces from 8.21 when used by itself for training to 7.5. We see this result as extremely promising, as it seems really the bottleneck for these performance numbers is the amount of data available. And so as more applications are included and more runs are included, we expect performance to get even better, and that we'll be able to train more and more complex models in the future. Next, we performed a similar recursive feature elimination to rank features for the application agnostic model. And surprisingly here, we see that num groups emerges as a highly important feature. In principle, one would expect that the placement of a job should have little impact on its performance due to adaptive indirect routing. However, in practice, it is possible that when a job is spread over more groups, the likelihood of encountering congestion on global links increases. We additionally notice the importance of stalls on global links, processor request stalls, and stalls on column links. In the next section, we show how we can use a small set of these significant counters to assist the job scheduler in making intelligent scheduling decisions. Finally, we show that by using the feature importances that we just obtained via the recursive feature elimination, that a trivial model that bins jobs solely based on their median values being all less than or all greater than the median for the top three counters and num groups, that we can bin particularly slow and particularly fast jobs into two groups, likely slow and likely fast, with statistically significant results. For AMG 512, likely slow jobs ran an average of 410.7 seconds, while likely fast jobs ran a full 30 seconds faster. Similarly, slow milk 512 jobs ran an average of 55 seconds slower than those that we predicted to be likely fast. Again, these results are really promising, showing that we can use the computationally expensive machine learning techniques in post-processing, do this work, build these models, and then use simpler statistical models in execution in the job scheduler where performance becomes a key concern. In summary, network congestion has a significant impact on application performance due to congestion on the system. A topology-aware resource allocator would be able to forecast varying performance needs and give better placement and scheduling for higher communication efficiency. A prerequisite to such an application is a strong understanding of HPC performance data, in which we answer in this paper. We show predictive models can be strong forecasters of the impact of network counters and show success in predicting the absolute execution time of a job based on system data strictly before the execution of that job. Thank you so much for the time. Please reach out if you have any questions, and please take a look at the other projects at the Parallel Systems and Software group at the University of Maryland. Thank you.